Good morning, everyone, and welcome to day 3 of Great Amrita Alumni Conclave, a full-fledged virtual webinar series spearheaded by the shining alumni of Amrita. The topic for today's session is the new age travel technology, and today we have with us our shining alumni, Mr. Vishnu Saseendran, Research Engineer, National Institute of Aviation Research, and Mr. Shreyas Narsipur, Assistant Professor, Mississippi State University. I would like to invite Vishnu to take up the session.
Right. Thank you. Thanks for the invite. I hope you guys can see my screen and hear me all right. Okay. Okay. Perfect. Okay. Thanks for the introduction again. And today's session, we're gonna discuss mostly about the new age travel technology. And I work in the aviation sector. I am a research engineer here at the National Institute for Aviation Research here in Wichita, Kansas, in US. And Before I jump in talking about these new age travel technology, I just want to put out a caveat. I'm just gonna focus just on the aviation sector, and I know I have my counterpart Shreyas here. He's obviously gonna cover more general on the other trends that is happening on the other industrial sectors as well. So what do I do, and what is my current role, and what does my organization do? I do not belong to an industry. I'm sure within this conclave series there are many industrial folks who will be talking about their work in the industry, and of course there are people from the university as well, like for instance Shreyas here. But I kind of sit in the sweet spot, if you will, between the university and industry. So we are an institute which comprises of about 21 labs, and we focus just on aviation sector. And we are located in Wichita because Wichita has a strong aviation community. It is called as air capital of the world because most of the aircrafts that you see in the world, be it Boeing, Airbus, Textron, like the Beechcraft, like the trainers and everything, they are manufactured here in Wichita. It has a strong supplier base because if you're making a big aircraft, if you're making a big aircraft, obviously there will be a lot of components, a lot of bolts, nuts, wiring, installations, you name it. So you have a very healthy supply chain here in Wichita as well. So it's a very strong aviation community. So when you have such large presence of OEMs, the original equipment manufacturers here in a town like this or in a city like this, you obviously would need strong research backing to solve industrial problems. And when you do that, you cannot obviously do that with a university setting, because in university setting, often the research are mostly scientific oriented. So what we do here is mostly applied research. So that's what I talked about, these 21 labs almost. And we are about 1,000 employees, was established in 1985, and we are spread across 6 locations, and we are always expanding based on our customer needs. Just to give a glimpse of how we are, we are not a conventional lab. It's an example shown here on the bottom left. So when the COVID pandemic picked up, the freighter, there was a need for passenger conversion to a freighter aircraft. That means you want to ship your goods from, I don't know, Europe to US or from Europe to India. So you want to do that quicker. So there was a supply chain disruption. So most companies, what they were doing is they were acquiring more aircrafts, and less passengers were flying. So they were taking all those passenger aircrafts and converting them to freighter conversions. So, but you cannot do that overnight. I mean, there is a lot of engineering work that goes behind it. There is a lot of certification. You need to recertify the aircraft. There is a lot of activities that need to be performed before you do a freighter conversion. So this, you can see that this is a former, I believe it was some Middle East airline that we purchased, and this is currently undergoing conversion as we speak. We also do special mods, like special mission aircrafts, like these are like one Bombardier and 2 particular 737s that are shown here in the hangar. So these are the kind of activities that we do here in our lab. So that's why I meant that we sit right between the industry and the university. And some of the images that I show on the right, these are from the local industry, like the productions that you see, like for instance, the green, that is the 737 hulls. The 737 is a Boeing's it is a Boeing's flagship aircraft, and it's actually one of the most outsold aircraft in the world. And we also have the 787 aircraft being also the Section 41 that is also produced here. So these are the these are the images of some of the aircraft, and this is how the community thrives here. So specifically, what I do is I work with composite materials. Composite is a lightweight materials because is a lightweight material because when you build an aircraft, you want the aircraft to be lighter. You want the aircraft to fly, to longer distance and consumes low fuel. So therefore, we use lightweight materials. They're called as composites, and I worked with composites. My PhD thesis was on composites, and I tried to come up with these test methodologies where I can improve failure predictions of composites. How can we better, understand the material? How can we better prevent failure in such materials? So those are the general area that I work on, and I work closely with the industry and our other, federal funding agencies. So that's just the overview of what my role and what the organization that I'm associated with do here in Wichita. Now, just I was told to give an introduction of how I reached here and what's my background. So I did my bachelor's BTech in Amrita University in mechanical engineering, and then I worked for about 2 years, one year in NAL, and then another year in the School of Biotechnology itself under Dr. Bipin and Salma at Amritapuri, and then before I moved to Europe to do my dual MS, and then finished off with a PhD, and then I moved here and joined this organization right here. So just to give a snippet of how Amrita would take you, or how I've taken, or how I've used what I've learned from Amrita. This is the project. I was surprised to find this when I was compiling this particular PowerPoint. This is a if you click this link, you can still see this particular project that we had done back in Amrita. I mean, I think I did some structural analysis of this particular project, and this kind of kindled my interest in structures and in more mechanics based analysis. And that sort of led me pursue my masters, and then sort of eventually ended up doing aerostructures, which is what I always wanted to do. So basically the foundation from Amrita is what got me here, is what I wanted to say. So just to give a shout out to my fellow accomplices. So I think except for Vishnu Hariprasad, who could not join, I think all three of us are actually giving these talk here. I think Shreyas will speak right after me, and Tejas is going to speak maybe 3 or 4 days from now, I believe, and he's going to speak about EV. So just to give a glimpse of where we are and what we do, and how grateful we are to have belonged to Amrita. Now coming to the session in particular, as I mentioned, I'll be just focusing on the aviation, on the newest travel technology specifically applied to aviation. So the buzzword in aviation here is eVTOL. It's the electric vertical takeoff landing. So if anyone have a smartphone or a gadget, I mean, if you just look at this eVTOL, it's what's happening here in the stateside, and also mostly also in Europe, but mostly in US. Is like the eVTOL market is taking off like crazy, and you could see. And this is not a rendering, by the way. This is an Airbus vehicle. This is an Airbus. I think it's called as Vahana. I think they're test flying this in Munich, and then the top one is a Bell design. So there are about 120 plus companies who are registered just to take this particular technology forward. And one of the unique things about this particular technology is that it uses electric engines, like these DC motors, and they don't use these conventional jet-based engines, which produces a lot of noise, and they are more intended to use like a taxi service. Like for instance, instead of commuting to, I don't know, maybe roughly 10 kilometers or 20 kilometers away, if that's a commute that you wish to make, instead of doing an Uber, in the future, you will be taking this air taxis as they call them. Now, there obviously comes a lot of challenges associated with it. We do work with a lot of folks, like a lot of industry folks who pursue this air taxis, and uh, and and these companies are mostly, they have automotive background. So what I mean to say by that is that the aircrafts that we see currently, they are produced maybe in 50s or 60s per month. So maximum you're looking at maybe 120 aircrafts per year. But these air taxis would be made hundreds per month. So that's what the intention is. So now the technology is being matured. Has been Now a lot of companies are doing their flight test. I think just yesterday another new company had released a design. So most of the companies, whatever they are doing, they're mostly in incognito mode, and they sort of come out, and then when their technology is in the readiness level of 7, we call it. So when it is SR7, they sort of come out, and then they either do a company listing, they do a test flight, and then gain more funding. So that's one area that is actually gaining a lot of momentum, at least here. It's a total buzzword, whether it be propulsion, whether it be materials, whether it be aerodynamics, whether it be avionics, like autonomy. Like, because imagine having these taxis, air taxis in your country, in your street. I mean, you would obviously need a lot of people to fly them, but I mean, if, I think it's a bane or a boon when it comes to pilots in aviation industry, because right now there is a lack of there is a pilot shortage going on right now for flying conventional aircrafts. So imagine if the market gets flooded by these air taxis. I mean, and so unless you don't have autonomy associated with it, I mean, it's pretty challenging to take this business forward. So that's definitely a challenge. And when that's one end of the spectrum. So if you move to the other spectrum, so these air taxis, mind you, they are like little hovering machines, but they are definitely faster than cars. So it would help you reach your destination faster. So that's one end of the spectrum. The other end of the spectrum is, like, for instance, you want to fly supersonic. I mean, I don't know if most of you guys know about it. There was a supersonic flight, I think, got retired in late 2000. Was the Concorde. We used to commute between London and JFK. So now there is a company out in here in Denver, right next door to us, actually. It's called as Boom, and they are actually producing these supersonic flights. But they want to make it such that it can fly within communities without having the supersonic booms affecting those communities. So it's a pretty cool technology and cool proof of concept that they're doing. In fact, I just wanted to make a just to show how we attach with these industries. So this is a wind tunnel testing of their concept, of this particular company's Boom's concept, that was tested in our wind tunnel. So wind tunnel is also a part of one of our labs in our institute. So like I said, so we work closely with the industry. We don't have any academic mission, so we just help them out. We just try to help them out, and that's what we do. So that's again, supersonic is one technology that is coming up, and so supersonic and these air taxis, I think I'm talking them. I'm probably one of us would fly them, maybe, you know, by before this decade even gets over, because that's the level of that's the that's the level of inventions that are coming in those fields. At the same time, it's rapid innovation, and it's rapid advancement, and it's rapid implementation. So it's going on a massive scale, and you will probably fly in either one of them before. I mean, I would say before 2035 for sure, but there is definitely a technology demonstrator happening, within a couple of years. Now going beyond supersonic, is another is hypersonic. That's when we call it more than Mach 5. It is 5 times the speed of sound. That's Hermes. It's another company based here in Atlanta, Georgia. So they want to go hypersonic, and obviously that would have other challenges. So now we are talking about traveling between continents in a matter of hours instead of or maybe less than an hour. I don't know. In supersonic, we are reducing the travel time from hours to maybe like a couple of hours. So that's the scale where we are going. Now, another challenge that aviation is facing right now is sustainability. I said eVTOL is a buzzword in aviation, but sustainability is also something aviation is pursuing really hard. I mean, this air taxi, if you look at all these designs, they are quiet. They don't have these gas guzzling engines. They use electric propulsion. So obviously, there is no carbon dioxide offset associated with it. So, I think the governments favor these kind of technologies. And if it can actually replace a lot of car commute, I think that would be great. So, but up until now, aviation industry, if you look at all these commercial aircraft, they have been pursuing they've been pursuing the agenda of sustainability, or they've been pursuing the agenda of low cost flying, not from the angle of sustainability. Like, what I meant is, I'm pretty sure you guys would have gone to a check-in counter and haggled for an extra baggage fee. That's because the airline companies, they don't want extra weight added to the aircraft, because if the weight goes up, then your business model, I mean, you burn more fuel, and then you make less revenue. So they would rather fly the aircraft empty than take you and take your bag along with it. So that's the so in order to do that, what they do is they kind of make the materials lighter, so that you can carry more weight and go long range and improve the engine. So that was a kind of associated developments that were being pursued until now, but it was not from an angle of sustainability. But with this COP26 and all the climate challenges that we are facing, I think, and with the air taxi developments, the sustainability has also become a key. Now, speaking about sustainability, there is a lot of innovation coming in this sector as well. So now aircrafts, instead of just not just with air taxis, there are plans to make I mean, actually use electric propulsion in bigger aircrafts, like the one that is shown below. This is, I think, it's an Israeli company. They did the taxi for this particular concept, taxi trials just last week. So it's a 9-seater aircraft, and it's a push propeller, two-engine propeller, and they have this electric motors driving it. The challenges with electric aviation or electric aircrafts in general is the weight of the batteries. It's okay if it is for a road commute, it's okay to have a heavy battery. But when you're really taking off the air, you would want that particular weight to be as low as possible. But this I would say, since this electric propulsion is used for long distance flying, it's still under development. It's not as developed as air taxis, because air taxis are literally, as I said, it's like taking off from one space and then moving forward and then landing from a short distance. Like it's like an Uber drive. Think of it like an Uber taxi. Now, if you cannot use electric propulsion, what next? So right now, lot of aircraft, they are trying to shift themselves to sustainable aviation fuels, SAFs as they called it. So by using that, they would offset the carbon footprint a bit down. They will be able to bring that a bit down. Now, another way of bringing in sustainability on a massive scale is to have hydrogen. Now, these two charts here show the concepts that Airbus have come up with. Now, hydrogen have their associated challenges. Like, for instance, I believe it was one of the car companies, one of the OEM car companies. They tried to bring in hydrogen in their car, but they found out that it's cheaper to power it use conventional electric motors rather than run it on hydrogen. So what I think the aircraft companies are doing right now is trying to use hydrogen as a fuel. Now, the energy density of hydrogen at ambient temperature is lower, so that means you will have to compress these hydrogen. And what the concept is that, I mean, if you look at the image on the right, what they want to do is, like, if there is an aircraft which comes and parks in particular aircraft, instead of fueling, you would just dock this particular hydrogen tank, like as if you would load a container with a bag or something. So that's what they are trying to explore. And when they do that, they want to make these developmental costs as low as possible, because you see aviation. because of all these strict certification and regulation practices, it's a heavily I mean it requires a lot of capital to make any developmental project. So you're talking about, like, for instance, if you take an aircraft like Boeing 787 or Airbus 320, the developmental time for such an aircraft is almost it spans almost a decade or a two, depending also on the test validation. And the development cost would run on the upwards of a couple of billions of dollars. So what they're trying to do is, if you want to explore the hydrogen technology, they're just using the existing airframes of, like, for instance, Airbus. They are using the turboprop. They have the ATR platform already, and when it comes to turbofan, they already have the Airbus 320 family, the single aisle concept. So they're using the existing test frames or the existing test beds, and probably make a little bit modification when it comes to for instance, the wings. It's I think they are from the 80s, so they make a bit of modifications, and they retrofit with the hydrogen capable engines, and see how the propulsion technology works. And then from there, they're planning to scale it up. So I would say this is still a nascence. This is still something that aircraft companies are considering for inter or transcontinental. That is between I don't know, maybe between Cochin and Delhi, or from here, New York to London. So that sort of flying is what they are looking here. So hydrogen is definitely gonna it's going to play a key role in the future. In the and Again, I cannot stress this enough. eVTOL, or the air taxis, that's the buzzword in the aviation. I think we have I lost count of how many companies have been listed here in the New York Stock Exchange, because that many companies have been listed, that many business models are coming up, and there are about 120 plus designs. When I say designs, like each individual designs of how the aircraft is going to take off, whether the motor will be tilted forward, or whether would you have a V tail, or would you have a combined rotor and a fixed wing. So it's a different ball game altogether. So that's the next gen travel, new age travel from an aviation perspective. So I just wanted to throw this out here. This is something that I found recently. Whether would you it's called as a hype curve, and in aviation, I believe it fits well, because we usually start in the lower belt. I mean, this is obviously, this stuff is for general discussion. We always start in the lower tier, where we have innovation, where there is media hype, and when you have a cool aircraft taking off, you have a lot of media reports coming in. So there is a lot of media hype, and the expectations sort of inflate, high, it becomes peaked, and it becomes all exaggerated. So we are in that peak right now. And I believe a lot of these companies are going for rigorous testing when it comes to avionics, when it comes to air traffic control. Would it be a nightmare? Because these air taxis won't be flying at 30,000 feet, where the conventional aircrafts are going to fly. So would it hit with another drone that somebody is flying? So all these questions are being asked now. So it's basically a technology demonstrator would actually maybe put a hole in that balloon. So once that inflated expectations would rupture, then we are sort of, it's a steep decline, where there is a dissolution of, okay, what is the reality? We face a reality. Can we take anything from this technology demonstrator and move forward? So probably the companies would have to rethink their business strategies, rethink their business models, and probably use handpick sort of technologies that they saw worked in the test programs, and then they gradually ascend the slope of enlightenment before going into a mass production. So that's the plateau of productivity. Now, before I sort of give the floor to Shreyas here for the other general discussion, I just want to throw this here for anybody who's considering aviation as a career, whether it be research, or whether it be just in terms of working as a day job, or I don't know, like or also managing this aviation business in general. So if you take the aviation, we can split it into manufacturing, propulsion, avionics, and structures. I mean, obviously you also have the branch of aerodynamics, but I just chose these just to showcase where I believe the next, the job or the talent pool would lie. What the next technologies, what will be the next technologies would be, and what are the next innovations and the technologies that are required to make this possible. So when it comes to manufacturing, we would need advanced materials because you would want the aircraft to be lighter. You would want like for instance, when it comes to hydrogen storage, you want the storing hydrogen is extremely challenging, and when it goes up in the air, when it is fitted onto an aircraft, you have these temperatures, thermal loading, all sort of complicated loading. So you want advanced materials when it comes to that, like carbon fiber based, and then you also need M&P, material and process engineering, because you want to make these parts as rapid as possible. You want to spend less time making those parts, and you want to produce it in a rapid pace. So for instance, this is a machine on the upper left, excuse me, on the upper left, this is a machine that we have in our lab here. It actually helps build these aircraft parts on a rapid pace. So basically, it has these carbon fibers. It is a lightweight material. So you just insert material onto this machine head and this machine, and you program it, and this machine will actually create aircraft parts. So this is one machine that we have in the lab. So these are the kind of from a manufacturing point of view, this is probably the direction. That is the direction where the industry is headed to. So these are the kind of skill sets that you would require. When it comes to propulsion, as I said, people are looking at flying up in speeds upwards of Mach 1. That's beyond the speed of sound, or Mach 5. So you would need new engine technology. You would need also alternate fuels. For instance, whether the sustainable aviation fuels can be improved, or can it be used at all in hypersonic engines. You also need high efficient energy storage, because I showed you an example of this particular electric aircraft here. This is only for nine passengers now. How would you scale it up to, I don't know, 30 or 50 passengers? So can you bring down? Can you have can you increase that energy capacity? Also new engine technologies. Those are the kind of fields I believe propulsion is gonna head towards. Now coming to avionics is basically you can think of it as a brain of the aircraft. For instance, if you look at the cockpit, what signal needs to be sent to a certain station in order to perform an action. That's basically the gist of avionics. Like for instance, you want to move a control surface. How would you program it? Now, when it comes to avionics, this is a bit more advanced. All the keywords that I've put here, like for instance, autonomy or cyber secure or cyber physical security. Like, can somebody hack into these systems? And obviously, I mentioned about the pilot shortage. So autonomy is something that air taxis would be pursuing for sure. So that's where avionics is headed. When it comes to structures, that's where that's my forte, or that's my field of expertise. So I believe in structures. Where we are headed to is we need more robust certification practices, because not everybody can fly these things. Meaning, you need to be there is definitely a safety concern. So you need to have rigorous certification practices before somebody can fly something that is of this revolutionary nature. Technology optimization, that is also another buzzword in our field. Like for instance, the image on the right here, you can see that it looks almost like a beak, like an internal web of a beak of a bird, like a hornbill or a kingfisher, if you will. This is actually a computer generated structure of an aircraft wing. So it is an aircraft wing of a Boeing 777 that I showed in the beginning. So what the researchers have done here is they've taken this wing, and then they are trying to they're trying to reduce the weight even further by allowing only material that is required, such that you optimize that particular design in terms of weight saving. So it's basically like a boundary value problem. You have your boundary condition, you have a load, and then you have the stress path. So you're sort of optimizing the control volume based on optimizer. So that's a massive field by itself. That's all the aircraft structures are being subjected to this topology optimization. This is actually, I pulled this from one of my previous colleagues. This paper was published in Nature, I believe. It's Niels from University of Denmark, or he was my previous colleague. So this is his paper actually, and it was a cool project. So we could clearly see this is one of the fields where the aviation is headed to. Then of course the usual topics of damage tolerance and structural health monitoring. So you would want to know how the material behaves. If you have a new material, you want to understand how the material will fail so that you can prevent that material failure. You can address it. You can prevent it from happening. If it happens, can you repair it efficiently? So all these are the areas where in terms of structures where the aviation field is headed to. I believe that's from my end. Shreyas, if you want to take the floor to contribute in the end.
Sure. So yeah, let me just go ahead and first start sharing my screen and right. Everyone can see it. Go ahead. So, all right. So yeah, once again, yeah, thanks Vishnu. And so yeah, like as Vishnu said, I'm here, I'm the second speaker in this particular section where I'm going to be talking more about the new age travel technology, hyperloops, and more. Vishnu, of course, went through more detail on, the eVTOL and the UAM sort of technology, and I'll be kind of going more of an overview with the basic structure being that I'll introduce that particular technology or the new technology that we are thinking of using, and then kind of going through the pros and cons of each of those technologies. So this is a quick outline of what I'm going to be talking about. So I'll go through a self-introduction, then go through the new age travel technologies, and more so, how can you get involved and work on, these really cool and new technology, that are coming up, in the future. So I'm currently an assistant professor in the aerospace engineering department at the Mississippi State University, and also I'm associated with the Raspberry Flight Research Labs over here, where I work on projects that are related to both subscale, which is unmanned aerial vehicles, as well as full-scale experimental aircraft testing. This was, very recently I joined this. It was back in 2021 was when I started this job. Before this, I was the director of aerospace labs and served as a teaching assistant professor in the mechanical and aerospace department at North Carolina State University, where I was handling the subsonic, wind tunnel, supersonic, as well as the anechoic chamber, which is an acoustic chamber facility. And prior to that, at NC State itself, I did my PhD in aerospace, which I got in 2017, with my area being in low order modeling of unsteady aerodynamics. Prior to which I was doing my master's in aerospace engineering back in the University of Illinois, where I did. So my work was more focused on wind turbine technology, specifically with multi-element airfoil wind turbines. But it all started, of course, at Amrita University back between 2006 to 2010, where I did my bachelor's of technology, and as Vishnu mentioned, did some projects too at National Aerospace Labs. Overall, my basic research interests are in applied aerodynamics, unmanned aerial vehicles, unsteady aeroacoustics, flight dynamics, and flow sensing and control. And to give you a taste of what I exactly do, or what applied aerodynamics is exactly about, what I do is use either computational or experimental techniques in order to really understand the flow physics of any particular of aerodynamic vehicles, right, or aircrafts or spacecrafts or what have you, and understand flow physics and then model them using low order or fast computational methods. So for example, in that simulation that you're seeing at the bottom over here, The background, all that colorful image over there, is from a computational simulation that, and this is for, imagine like, or your wing or a helicopter blade that is, in an unsteady motion, or, it's going pitching up and down, or, about a particular point. And that computational simulation, which is all the colored pictures in the background and the pretty pictures in the background, that took around, for this particular case, takes around 30 hours, right? So and it's a basically high fidelity computations. But then the low order method that I developed as part of my PhD work and postdoc work, which is the white and the black dots that you see at the background, took 15 seconds. To basically, we are able to reduce the amount of time for fast simulation and design and development purposes. So that's the kind of field that I'm continuing in. Of course, I'm expanding not just from unsteady aerodynamics, but also going into, like some of the topics that are related to unmanned aerial vehicles, like prop-wing interactions, aeroacoustics, flight dynamics, and of course, using all of that for both prediction and control methodologies. So moving on to the topic of the day, which is new age travel technology. So again, like I said, I'll be giving a more of an overview of all of these things. So what is your motivation, right, for new age travel? I mean, we have boats, we have sea travel, we have train, we have roadways, cars. But what is the motivation? Of course, aircrafts, of course. But what is really the motivation for moving forward, right? And essentially, it could be you want to go faster, you want to be cheaper, you want to make these things cleaner, or you want to make it more safer, right? So either all of these or a combination of these are what really motivate going into new age travel, right? So technology never stops. You want to keep making things better, faster, better, cheaper, cleaner, and all of that. So, and of course, sometimes even responding to the challenges, current world challenges, right? For example, the cleaner part of it is a big response to global warming, right? So, so a lot of motivations that come in order to develop new technology, right? Now, the current big technologies, I mean, of course, there are a plethora of them, but the ones that I'm going to be focusing on are, self-driving cars. These are, I think, some of the things that we are hearing a lot more these days. So we have self-driving cars, we have the Hyperloop, we have supersonic jets, and urban air mobility. The last two of which I think Vishnu covered in more detail in his presentation. So what are the considerations that you have to take while trying to develop these technologies? So one, of course, is the technology itself, right? Because sometimes what happens is that it just, technology, like the new technology that you want to develop depends on what is available, right? Or if it's not available, you have to develop that particular technology, and then it can probably affect everything else. For example, in aerospace research, computational research was there since back in the 1950s and 60s, right? There was a lot of experimental research being done, and then computers were developed, and then you start doing computational simulations, which is the kind of what I showed you in the background. But at that point of time, back in the 1950s and 60s, you obviously didn't have much of computational power. So the amount of computational analysis that you could do was very limited. But of course, in today's world, the speed, the amount of computational power that you have improved, and because of which a lot of the problems that were already solved, are being resolved now, but with better technology, right? And the same thing goes for even new technologies that come up. So one particular improvement in one set or in one research can actually affect a whole bunch of things. So that's one consideration. The other one is, of course, environmental, and then you have economic and even social considerations that need to be taken into account before all of these technologies actually become a reality, right? So right now, the stage that we are at of what we're going to be talking about are all in the phase where the technology is present or it's being developed to, to a mature level where it can be developed. But there are still a lot of economic and social and environmental considerations that are being done before it can actually be implemented, and kind of goes through the same, I kind of like that curve that Vishnu showed up. That was where we are here, where we are trying to reach the peak of it, but it's going to fall, because that's when the environmental, economic, and social considerations start to kick in, and they need to be solved before they actually become full-blown realities. So going into self-driving cars, self-driving cars are not a new concept, right? It existed since the 1920s, where there, of course, there were cars in which electric cars, in fact, that were asked to follow a particular road path and so on. I think it was by GE or GM, one of them. They started to become more feasible due to, better computational capabilities. Again, new technology, GPS, LiDAR technologies. And I think, back in 2000, sometime in the 2000, DARPA, which is a federal agency over here, introduced a challenge to make autonomous cars, right? And that's that left, image on the left-hand side over here. And so, yeah, the technology has been there. And again, as and when newer techniques have been developed, newer research has come out, new subsidiary technologies have developed. For example, the electric vehicle technology, this thing, self-driving cars have started to become a lot more of a reality. Self-driving cars, at them, it's almost right now, it's at that peak of actually becoming reality because with, electric vehicle technology, you have lesser number of moving parts. So this particular car, the Hummer that you see at the left-hand side over here, is your normal traditional car with gears and a lot of moving parts. But then with electric vehicles, you have much lesser number of moving parts, because of which it starts to become a lot more feasible to have these self-driving concepts. What are the pros and cons? Pros, of course, if say you have self-driving cars everywhere now, pros are that a machine end of the day makes a lot lesser number of mistakes, right? So that's one big pro. Fuel savings, because the lesser the number of mistakes you have, you're always driving at a more optimal level. So you can kind of optimize the fuel consumption, and therefore there'll be fuel savings. It's obviously faster. For example, if you have only self-driving cars in the next 10, 15, 20, who knows, right? How many ever years, at that point of time, your speed limit does not need to be 60 kilometers per hour, 80 kilometers per hour, right? Because everyone is driving this, self-driving. If everywhere, you're flooding it with self-driving cars, everyone can go really fast because there are lesser mistakes being done. You have better air quality, of course, because you are optimized in driving, fuel savings, and therefore the air quality is improved. You have lower operating costs because, again, optimization in the whole driving technique. You have lesser fatalities and improved mobility, specifically to people who really cannot drive cars. So big pros there. But at the same time, there are cons too, right? And that's where the economic, social, and the environmental concerns start to come in. One is, of course, it creates unemployment, right? You have a lot of taxis out there today. What are people who do that job? What are they going to do next, right? So that's the one part that always needs to be looked at. You have high research and development costs, which obviously is going to reduce right now. And that kind of ties into higher purchase price too. New technologies always come with a very heavy price tag. But hopefully, as it becomes more and more of a reality and the demand increases, that should start going on. Now, hacking issues, of course, in Internet of Things, it's so easy. Everything is connected, right? So it's so easy to hack in and pretty much just make you go in a completely different direction. Actually, some of these cases have started to happen. So that's obviously something that needs to be looked at. It's obviously weather dependent because, all of these cars, self-driving cars depend, or robots or whatever it is, depend on sensors, and they can all be, sometimes in snow, rain, or what have you, they can not be performing to the optimal level. The other big concern is people may not accept this technology, right? It's the same question that happened in the elevator. Initially, when the elevator or lift was introduced, people were absolutely not ready to, even step into it. But it just takes amount of time, right? In this case, people are not you're so used to being in control that just trying to leave a steering wheel and let things go might not be, it's kind of a psychological battle too that you have to play with. And that's one of the, it's just not with self-driving, but every technology, there is a psychological study that needs to be done so that people can accept it. And then, of course, you have regulatory issues because all of these benefits, big benefits of self-driving cars come because of, your, that all of the cars have to be self-driving. That is when all of these benefits can be realized. But then if you have some people who don't want to do self-driving, you're now trying to combine efficient cars with people, people driving who can make emotional decisions, right? So that becomes a big con. Moving on with the Hyperloop, of course, the Hyperloop is, it was created and paid. Again, these are all things that have been looked at back in the 18th century itself. It was a patent idea of a railway to move people or cargo through pressurized or evacuated tubes. And the way it was done was using a vacuum tube, which would substantially, which made the whole system substantially free of air resistance or friction. It became more popular back in 2013 when Elon Musk, who's the founder of Tesla and SpaceX, introduced it as a fifth mode of transport after planes, trains, cars, and boats. And there are a lot of commercial entities working on technology, which include Virgin Hyperloop in the US, Transport Canada, France, DGW Hyperloop, which is just in your backyard in India, and of course, Arrivo in US, to name a few. Pros and cons with this again. On the pros, very, very high speeds. You have low carbon emissions, like with any public transportation, and of course, the vacuum chamber. There is, I mean, it is based on magnetic levitation technology, so very low carbon emissions. They are weatherproof because it's all underground. They are less invasive. Once again, it's not about ground infrastructure, right? So you don't need to worry about that. So it's very less invasive and much lower operating costs. But on the con side, very high infrastructure costs to build it itself, right? You got to dig a hole underneath, and there are a lot of other structural environmental issues that need to be taken into concern. There are safety concerns, of course, because it's hard to communicate and it's very hard to evacuate if something goes wrong in the middle, and it's inflexible to demographic changes. So demography always changes from, one region might be very populated at one point of time, but things can change around because of whatever disasters or whatever other issues. So trying to change this whole system might become very difficult. Next is supersonic jets. Vishnu did touch upon it. These were previously explored and commercialized back in the 1980s. The two most popular ones being the Tupolev Tu-144, which was from Russia, and Concorde, which in my opinion is one of the most beautiful aircrafts that was ever built, but unfortunately could never be commercialized or be used to its full extent. And the reason being was that it had very, very high operational cost and very low acceptance of the technology by people in general. This is, of course, this whole concept now has been reinvestigated in recent years due to advances in research in the aerodynamics, structural, and the control technologies. And again, it's always that research cycle, right? New research, you revisit the old technology probably for better benefits. Pros and cons in this case, you have very, very high speed. Supersonic in general fly, faster than the speed of sound. I think when Concorde was developed itself, it used to fly around 2 to 3 Mach, which is 2 to 3 times the speed of sound. So very, very high speeds. So therefore, it can ferry more number of passengers. And then it's been known that these are all very efficient over long distances, and therefore less cost per kilometer, which essentially, end of the day in aerospace, one thing we all realize is everything comes to the money amount, right? Whether you're reducing weight, you're reducing the amount of fuel, you're making it cleaner, it all needs to be justified based on the amount of money that you're spending. So that's a big, big push. I think it's any technology, and is more specific to in aviation. The other cons, of course, there are very, very high operating costs. That was one of the big failures that happened. It was, I think, one single accident or one or two accidents that happened on the Concorde that completely downed it. And so they're very, very high operating costs. There are a huge amount of noise concerns because the moment you hit, you go above Mach 1, there's something called a sonic boom that occurs. Without going into much of details, that basically creates a huge amount of sound. And that's one of the big noise concerns that kind of did not allow the Concorde to operate, between major cities. I think it could go between New York and LA, at least in the USA, but then other noise concerns because of the sonic boom, it was not allowed to fly over highly populated areas. And it's not efficient at lower speeds. Again, without going into more details, basically there is a big design philosophy difference between low speed or subsonic aerodynamics and supersonic aerodynamics. And the supersonic flights are not efficient for low speeds. And therefore, that kind of translates to poor range. They're good at high ranges, but not at the low range sections. And they have very high environmental impact just because the amount of fuel burn that they have, as well as, of course, the noise concerns that go with it. The last one that I'm going to be talking about is urban air mobility, right? So this is, again, Vishnu covered this, and this is where all the eVTOL technologies are coming in or being looked at. It's mainly for the urban air mobility concepts. So I'm not going to spend too much time on this, but the main focus of this urban air mobility was developed in response to huge amount of traffic congestion in large cities. And the main idea for this was to be used for commercial or intercity travel. So you have short distances, for example, between Bangalore to Mysore, or, your Kollam to Trivandrum, those kind of commercial intercity thin haul routes. That's where this wants to be used for cargo delivery, public services like air taxis, and of course, private and recreational vehicles. Pros and cons again. Pros: faster transportation, lesser congestion, much better connectivity, and reduced emissions, especially with that electric VTOL technology coming in. Very, very less emissions will go in. But again, the cons are they are weather dependent, right? There's a lot of research actually going. In fact, my group is actually working on this where, in what kind of weathers, because what happens is weather has been very, very well understood for much larger scale aircrafts, but for these smaller aircrafts, these weather concerns are a lot more because they're smaller and therefore the weather can actually affect it. And also they fly at a much lower, height, which and therefore the lot of in the lower regions of the atmosphere, the weather is predominant as compared to in the higher stratosphere regions where normal aircrafts fly. You have, of course, noise concerns because these are all going to be within within the city limits, and that's one of the acoustic research that I'm working on to see how you can actually reduce the noise. You have regulatory concerns because all of these have to fly in the same airspace as larger aircrafts, right? So you want to make sure that there are no disturbances or crashes and safety concerns. And that, yeah, like I said, that's the next point, which is the safety concern part of it, not just with other aircraft, but also, having it, because if it crashes over here, it crashes right in the middle of a big city. And finally, it's highly infrastructure dependent. So, building all of this stuff is going to come in. So these are all the cons. Again, cons are again just opportunities for us to be looking into research. So those are the things that need to be looked into or being looked into currently to make urban air mobility a reality. With that, go to the last slide in my talk, which is how do you get involved in whatever of this research, right? Or, I mean, it's kind of how did Vishnu and I kind of get into this field. And some of the basic things that I have at least learned as part of all of this is these 4 points, a few points that I'm going to go through. One is number one, and I think I'm given to understand that most of you all are in your 11th and 12th grade, and I think this is where you build your foundation. So my first advice would be to focus on fundamentals. Engineering, end of the day, is just application of your basic physics, chemistry, math, and your basic science and math knowledge, right? And what happens with engineering, one thing I've noticed is, as I teach students, undergrads and graduate students, during your 11th and 12th grade, all the concepts that you learn, for example, your Newton laws, right? You have 1 year to really absorb that concept. But the moment you come into engineering, you have 6 months to just apply those concepts in a very number of field. In one semester, you'll be doing fluid mechanics, statics. But under bottom line, if you actually break it down, they all are basic Newton laws, right? Believe me, number of times, one problem that I looked at, that you break it down, it just becomes F is equal to ma. It's pretty much as long as you're within the atmosphere, F is equal to, those 3 Newton laws are all that you work with. So focus on those fundamentals, because those are if you're able to you're very strong with that, that is what will take you to the finish line and make you a much more successful engineer. The second one is, as you saw in all of these things, and based on what Vishnu also said, all of these are very interdisciplinary sort of research or topics that you look at. So don't just focus on your major degree. For example, and this happened to me. I was a mechanical engineer and I thought, oh, you know what? I'm not even going to care about computer science, electrical controls, or what have you. But I realized, very soon, once I finished my bachelor's and I went to my master's and PhD, I realized that if I cannot just be in my own cocoon of mechanical and aerospace engineering, I need to actually look more way beyond. Aerospace in particular shows you that, because it is a very clean amalgamation of mechanical engineering, structures, aerodynamics, fluid mechanics, and controls, right? Electronics being part of it. So look beyond. Yes, you're focusing on one thing, but always keep your minds open to things. Third one is pursue external opportunities, like Vishnu mentioned in his slide. While I was in undergrad itself, I was not just looking at just what I was doing in class, but looking at what I can do beyond that. Because end of the day, when you become an engineer, there are lakhs of engineers that graduate in 1 year. You need to be looking for opportunities that make you different from everyone, because that is what is going to get you to that next level. The next one is always ask questions. Don't ever be afraid to ask questions. It's okay even if they are stupid questions, but ask them, because that's the only way you learn. Moving on, and kind of talking more about learning. make sure you learn that art of Googling. Today you have, I mean, this is more so, I mean, I've kind of seen this go through. When we were, when we were doing our undergrad, it was even so difficult. I don't think we even had, that easy access to laptop. But today you have so much of information at your fingertips, right? Learn to Google. If you have a question, Google that. Ask questions and Google it. If you're not able to find that, then just keep find. There are so many resources. I can guarantee you, you have a question, there'll be an answer out there. So learn that art of Googling and never stop learning, right? I mean, that is one thing that I always found that, because the moment you don't stop learning, you always are trying to explore newer and newer things, and you never stagnate in your life. And that is, I think, that, keeping your mind, running at every opportunity that you get will not only help you, just be so active, but also be able to, push you to those, the edge of technology where you are at that, at that frontier and pushing it to new levels. And finally, think big. Yes, like I remember when I was in my, I think even before my started my undergrad itself, I knew I wanted to do my master's, right? Yeah, it's like a 5, 6 year plan, but always have that final goal in mind, because once you have that final goal, then start, you'll know what exactly are the steps that you need to get to that particular point. So don't ever restrict yourself to thinking, right? I mean, of course, I didn't know back then that I'd be in the position that I'm in. In fact, I didn't even think that I'd be as a professor, right? I always thought, oh, I'm going to go into the industry, I'm going to work, but I never even imagined that I'll be a professor doing this sort of really cool research that I'm currently pursuing. But the only reason I was able to get to the position that I'm in is because I never restricted myself. It'll be scary sometimes, but that's okay. It's good to be scared, because only if you're scared, you're trying something new. And when you try something new is when you're going to be at that frontier, pushing the boundaries of science, aviation, research, whatever technology that you end up pursuing at the end of the day. With that, I'll end my talk. For questions, and any questions you have, please feel free to contact me on that email ID. And with that, I'll hand it over to Nija. Thank you so much.
Thank you so much, Vishnu and Shreyas, for a very informative session and sharing your experiences. So, before we end the session, we would like to hear a few from you on how your life at Amrita was. So, I'll like to start with Shreyas.
Yeah. Um, yeah, I mean, like I said, I think the 4 years that I spent at Amrita, I think that, I mean, that's easily what, built the foundation to which I was, to what I was doing here. And I think one of the biggest, the best things that I got out of it was the people that I was surrounded with, specifically, the current dean, who is, I still call him Bala sir, Dr. Balkrishna Shankar, and Josh Freeman at that point. Josh, there were a lot of labs that were allowed to associate with. I think we were one of the first few batches of mechanical engineering that came through, and there was so much of positive energy and positive push for us to go beyond and achieve something. And I mean, and in case there was an opportunity that we found, no one, I mean, everyone was there to only encourage you and push you to that next level. And I think, I mean, long story short, if Amrita had not given me the foundation that that it did, I don't think I'd be doing the thing I'm doing, the things that I'm doing today. So, yeah.
Thank you so much, Shreyas. May I hear a few words from you, Vishnu, on how your life at Amrita was?
Was always yeah, it's a well, I mean, social life was always happening, but I think when it comes to building a career, I think Shreyas mentioned about it, all the foundation was given to all the foundations that I had or that garnered was from Amrita. I think something that I would like to point out is often we kind of overlook the quality of faculty members that we have at Amrita. So even when I did my PhD or my master's, like what I learned during the undergrad, which was I could take that and use that for during my studies, during my master's and PhD. And I mean, it's because I had that particular foundation, which was imparted by these great folks. Like Dr. Bala, Dr. Sundar, like Dr. Ganesh Udupa, Tyagaraj. I mean, you have different courses in Amrita, and each one of them are handled by these guys who are top of their field. I mean, they have they have excelled in their own fields, and they have come back and they were giving it back to the community or giving it back to us. So it's because of them that we are what we are. I don't know if we are at all where we are, but if at all it happened, it's just because of them, and we owe a great deal to them. And of course, a lot of opportunities opened up because of them, because of the contacts, because of the networks. So yeah, it is definitely a great place to be. So if you guys are going to Amrita, yeah, I would not hesitate to to give a recommendation. Yeah, for sure.
So thank you so much, Vishnu. So once again, thank you for a wonderful session, and thank you everyone who are watching the session for spending your time and joining us for Great Amrita Alumni Conclave. So that's all we have for you today. We'll see you all for day 4 of Amrita Conclave. So till then, have a good day. Thank you.